Welcome to our webinar today, CPK, What's Its Capability? I would like to welcome you all and thank you for taking the time to join us today. First, I will address some of the logistical issues for the session and then introduce our first speaker, Forrest Breifogel, and then our second speaker will be Rick Haynes. We have a lot of material covered over the next hour, and so we will be muting the audio for the remainder of the session so that we can get your text questions, but we will not be able to hear you over the audio portion. So please continue to send in your questions through the GoToWebinar service that you have in the corner of your screen. You can send them throughout the session or at the end, and we will either address them at the end of the session or contact you offline. There will also be a recording at the online resource library available in 48 hours. This link to the recording will be in the email that you receive tomorrow. So just to let you know, it will be delayed. You won't get that information until tomorrow. Please know that as a participant in this webinar, someone with Smarter Solutions will be giving you a call. If you do not want us to contact you, please let us know in the feedback survey at the end of the webinar. I will now introduce our first speaker, Forrest Breifogel. Forrest is a professional engineer, ASQ Fellow, and serves on the Board of Advisors for the University of Texas Center for Performing Excellence. In 2004, he received the Crosby Medal for his book, Implementing Six Sigma Second Edition. Forrest has authored or co-authored 11 books and published over 70 technical articles for his well-known worldwide publications. He is the founder and CEO of Smarter Solutions. He has recently published a 4-book series on integrated enterprise excellence, which is now available. I will be now turning it over to Forrest to give you a little bit of insight into CPK.
Hello, this is Forrest Breifogel. I really appreciate you taking the time to be with us today. The topic of today is one thing that I really have a passion about here. It's really important to have metrics that provide easy to understand insight to what is happening in the processes. However, really over the years, I found that this often does not happen, and there's really a lot of confusion relative to process capability indices. We'd like to have a system so that when we look at a process, no matter who looks at the process, the only difference is in their assessment of it would be because of chance. Somebody might get a better set of numbers than another person. But a lot of times CPK and other process capabilities can give you a distorted picture of what's really happening in the process. So Rick Haynes has done an excellent job of putting together this particular webinar that describes some of the issues that are prevalent with CPK. So I'm going to be turning the mic back over to Mallory here, who will be introducing Rick Haynes, who will be providing the information to the remainder of this webinar. Thank you.
Thank you, Forrest. I will now be introducing Rick Haynes, as Forrest mentioned. Rick is a 19-year Lean and Six Sigma practitioner and one of Smarter Solutions' senior instructors. Through his career, he has certified as a Master Black Belt, Champion, and Yellow Belt, along with teaching and certifying professionals in all the Lean Six Sigma areas. His personal Lean Six Sigma work has spanned nearly all business types: manufacturing, transactional, along with research and development business. He is a master degreed statistician and has taught statistics in the Penn State University system. He has worked in all levels of business, from the entry level up to a site engineering manager. His life experiences and skills will provide you with an engaging discussion of the frustrations facing businesses today and learn a little bit more about some of the tools using CPK. I will now turn it over to Rick.
Hello there. Thanks again for joining. I'm Rick. CPK is a wonderful topic, so we're going to go into it here. What I'm going to talk about is somewhat of the theory. I'm assuming everybody doesn't use this every day. We're going to talk about confidence intervals, which will probably be new to all of us, including me when I started looking into this. But it makes sense. We're going to talk about primarily when you don't have pretty data or it's non-normal. Mixtures and non-normal. We'll define them when we get there and do it. Mallory was right. We'd really like your questions as you go through. Just type them in. There's so much more to talk about than what I have in the prepared material. So the questions will fill out some of the neat topics I may have skipped over. It's hard to talk about something you really like in just a few minutes here. Next one, let's look at the theory. CP and CPK. I guess I've been using this forever. When I started way back in manufacturing, we had CP and that's all we used. I remember the introduction of CPK and how it was the new and greatest thing. And it was leading. Our suppliers had never heard of it, but it was an interesting thing. We liked it. It seemed to be everything we needed, but we struggled with it. And so we'll talk about some of that as we go through here. But first, let's define them. CP, people talk about that as the capability index. It really is, can you fit the process in the specifications? Note that it requires an upper and lower specification. So some of us can't use it because of that alone. But also doesn't talk about centering. You can have a great capability, just not be centered and still be all bad. So it's really just looking at the widths. And for all of this, we'll talk about the width of a process as 6 standard deviations. If you think about a normal distribution, that's supposed to be 99.73% of the data, so that's really all of it. Now CPK came up later. And why? Because CP didn't involve, was it good or bad? So when we look at the CPK, I have up here the equation we probably all learned at first. The minimum of the capability against the upper specification, the lower specification. So it looked at the worst case, but realize from here, if your process hung over both specifications, it ignores half of the problem right there. And I guess it's maybe not half because it's close. We always deal with the one that's the worst case. But if you're in bad shape, you've got out of tolerance material on both ends, and this does ignore it. So that's a known. But we're going to go beyond that here. Now, how many of you wondered, why is there a K? Well, this is something I found interesting. There's people like me out there that enjoy knowing why everything is the way it is, and this was part of the fun. So I want you to look at this. It really, CPK is the CP times 1 minus K. It makes sense. Well, what's K? And you can see the equation there. It's got two things you got to calculate yourself, but it uses the absolute value of M, which is the middle of the specification, to calculate it. So it really is a correction factor for the CP. Now, isn't the other equation better? You bet. But I just wanted you to see where it's coming from. Now, this is what we don't talk about much, and I probably didn't learn until I was going back to school. The assumptions of a CPK. Well, first one is it's normally distributed. If you step back, it's all based on a 3 sigma limit we consider good. Well, that only means something if you've got normally distributed data. Next one is it's supposed to be independent, uncorrelated to be the statistical terms, but the idea is it's a random set of data. So it truly randomly represents the process. Now, I like to use that it's a representative rather than a random data set because it implies a bit more, but you have to have a good sample to make it even close to reasonable. And the last one, I swear we never talk about, is stable. If your process isn't stable, you shouldn't be reporting any capability estimate, CPK, percentages, anything, because who knows what's coming. And people take the CPK or any capability measure as an estimate to make business decisions on for the future. People aren't really as concerned about what happened. You already know that. But these are to be used for business decisions for the future. And when you realize that what we're really trying to do, all capability estimates are at risk unless you meet the stability estimate. If you are a Lean Six Sigma practitioner at some level, you may realize that those three are almost the same conditions we have for most of our testing. T-tests, F-tests, so this shouldn't be new. I mean, we use mean and sigmas, so really you can treat this somewhat the same as you do all the other testing we do, so this really isn't new. Now, why do we care about these? Well, the normal one's probably the easiest one to talk to. If it's not normally distributed, the whole concept of a CPK of 1.0, which means the specification is 3 standard deviations away from the mean of the process, doesn't mean we're good, or doesn't mean we are as good as we may think. We basically think the 3 sigma limits are no defects, but we would know they're 0.27% defects. So, do most people use it this way? Well, if it is, I propose it's by chance. Most practitioners, including me, don't think about this sometimes when we're using a lot of our tools. We meet the assumptions because sometimes things are normally distributed and stable. But without checking them, you are at risk. Now, when you get a high CPK then, and you really haven't met your assumptions, you would assume a near 0 out of conformance condition, but you're not getting it. I spent all out of my early life as an engineer wondering why we could have a CPK above 1 and still have defects. And not just 1 or 2, but routine defects. It was years later when I understood how that can happen, and we're going to talk about some of that here. So what was really wrong? Well, it wasn't normally distributed stable data. So I guess I gave it away, but let's talk about it now. We have a little survey question for you here. It helps me understand where we're going based on how you might describe yourself. I'm always interested in who chooses to listen to these things. So please pick one. In a little bit, I'll tell you how it turned out, and you'll all see the histogram of participants. Let's see. About 2/3 of you have voted. Come on, the rest of you. I hope you're paying attention. All right. Just got a couple left. We'll close off the poll here in a few seconds. All right, we're done. Let's see how it turned out. Well, we've got Lean and Six Sigma practitioners are our biggest piece. A couple at the executive level. And I'm glad to see some that even have no experiences, because there's probably some out there that just thought CPK. I've heard people talk about it. What is it? We're going to help you all out. You may be the smartest person back at work after hearing this. All right. Let's look at the next one, confidence intervals. We usually take for granted confidence intervals of means and standard deviations and coefficients and everything when we're doing our statistics, so, excuse me, the statistical parts of Lean Six Sigma. It's easy, but realize you can do a confidence interval about anything that you calculate. Well, CPK is just a calculated statistic. So it has uncertainty, and we don't think about that much. So let's look at it. Now, this is where I guess I should come out and say that I'm a nerd. This is really a big thing, but we're going to dive into the places where you don't usually talk. And I have to admit right now, I'll say it, I am a reformed CPK user. It was very important to me earlier in life, but I have broken the habit as I learned to understand what it really means. So I hope that you walk away with this knowing what you can really do with this term. All right? Here's the equations for the confidence intervals. I'm sure that's pretty to you. The Z is the same thing you use in a normal distribution probability table. You can see CPK. N means sample size that you use to calculate it. The little CPK with the hat over it means that's the calculated value. And this would provide the confidence interval for it. What I always ask of students is, does this make sense? Because I read it out of a book. I probably found 3 sources that confirmed that this is the equation to use. And so then I took it and I did using a software called At Risk, and did a simulation, because I really don't trust any equation until I can prove it to myself. My skills did not allow me to rederive it, but with these simulation programs available, you can test things like this really quick. About 5 minutes, I could test all these and show that this equation is proper. Okay. What it does show, though, is large sample size, you have less uncertainty. And when the CPK gets higher, you have more uncertainty, but again, that makes sense because you're way out in the tails, and there is more uncertainty on the tails with distribution. So what is the impact to us? Knowing that there's uncertainty, I put this little plot together from the equation. I chose at 1.3 to be the center line because that's what most businesses say their target is that use CPK. Where CPK of 1, meaning I'm right at the edge of my tolerance, is usually where we want to stay above. If you look at this chart, until you have a sample size of 40, when you calculated a CPK of 1.3, you still have a chance your distribution or your process is producing product with a true CPK of less than 1. Look at this curve, it's pretty dramatic. I didn't realize the uncertainty involved. If you look at it clear out to a sample size of 100, which most of us don't take time to collect that much, the CPK that you calculate still has an uncertainty of plus or minus 0.2. And this is again using 95% confidence intervals. So using a sample of 10 to 15, which I believe what my history was, what most of you might use, you really don't do well with a CPK of 1.3. You have a risk of significantly still having bad product. This is one of the reasons my history had defects with a sample showing a good CPK. Now, how can we look at it another way? This is probably more, because I would propose that CP and CPK are used so people can take a simple look at it, but the real issue the business cares about is your non-conforming fraction, or the percent defective. And although it doesn't say it here, Smarter Solutions does recommend that if you're talking capability, the right thing to do is to just talk about the long-term predicted percent defective. And you do that with probability plots and some other tools. But admit some of us have to speak to what the leadership wants, and this is where we're talking about CPK. So in this chart, I assumed that you calculated a CPK of 1.3. How bad could the true long-term defect rate of your process be? So really, we used the assumption of normality and backwards from the CPK to calculate a mean and the standard deviation. We could calculate the percent defective. What you look at here is with a sample size of 10, which is common, you could report a CPK of 1.3, which your leadership would say, I have no defects. But the process could still be producing a 1% defect rate over the long term. So again, this is how it can make you feel good and sometimes not be good. Please don't forget to put in questions if you have some. Now we have another survey question. This one about why are you here? Why are you listening? It's always interesting to understand what draws people to these. So please, again, take some time, answer the question. There's a third of you. All right. We're up to 3/4 already. Thanks for doing it. We'll close it in here in about 5 seconds. All right. If you look at this, most of you are here just to continue your education, which is important. Just general interest. And there's about a fourth year looking to improve your personal skill level. That's a great thing. You always should be working to improve yourself and learn more stuff. And I see there's some of you even looking at CPK as possibly a way to improve the whole business improvement effort. That's great. Thank you for that. And again, please type in questions. Next one, mixtures. Oh, what's a mixture? Well, a mixture comes about when you've got data coming from multiple processes and they're combined together into one output. Right? It comes when you have, it could come from multiple machines producing the same products because you have greater capacity. It could be from 2 locations processing claims for your business and they all work slightly different. Or even 3 shifts running the same equipment. They all get combined together. In the case is where your customer sees them all as identical, but you know that they are coming from slightly different processes, different in that they might have a different mean or a different variation. Okay. As you can expect, stating it this way, most high-level business processes are actually mixtures, especially the stuff the customer sees. Okay. They can be bimodal, one we talk about a lot, or multimodal, meaning it's 3, 4, or 5 little distributions all combined together in the view of the customer. But either way, it's just data. Now, how will we measure its impact? I did it through, again, using the at-risk simulation software because it is really perfect for these type of things. What I did is I assumed we had just bimodal, since it is easier to deal with. But I took 2 normal 0-1 distributions. And what I did is I would run them 4,000 times and measure the percent out of spec, the Cpk, and we'll see the stuff. But then what we did is we'd run the simulation again, slowly moving the 2 distributions apart. Each distribution was about half the data. So I took the shift between them of 0, which meant they were the same, up to a difference of 4 standard deviations, or a 4 sigma shift between them. With that, I calculated the Cpk and the true percent effective of each case. Now here's an aside. What's enough shift for 2 distributions to look bimodal? All right, let's look at it. I hope these lines are thick enough that you can see them on your screen. What we have here is 3 different combined distributions of 2. And if you look at the 1 sigma one in the upper left, it still looks nice like a bell curve. Now when I get to a 2 sigma shift, you can see it's starting to flatten out. But when I get to a 3 sigma shift, it's clearly got 2 humps. Interestingly enough, it is about a 2 sigma shift where you start dramatically leaving normality, and you see it as a bimodal distribution. And a 2 standard deviation difference between 2 processes is really large, so it's surprising. By the way, these charts were generated with a teaching software called Fathom that does dynamic graphing. It's great if you're trying to teach a lot of the concepts to show real-time charting change. Now here's how I went to analyze this. Again, using the at-risk software by Palisade, we did a simulation. So we did it with 2 different sample sizes because we can recognize larger samples should be more discriminating. So we did 25 and 50. Both distributions had a standard deviation of 1. I did an off-center specification for this because Cpk is a one-sided tolerance measurement tool. So we did a minus 2.8 to 3.2. Recognize being centered with at 0 with a standard deviation of 1. The width of the specification and the width of the distribution are equal, so I start with a Cp of 1 in this case. Then what I did is I shifted the means apart from 0 to a half to 1, and you can see up to 4. Ran each 4,000 times and collected the results. By the way, it took about 7 minutes to run the whole simulation through all those pieces. And it outputs to Excel. It's real nice. So using that, I collected the estimated Cpk of each of the 4,000 samples with each shift. With each, I calculated the percent effective given that Cpk and normal data, and the percent that was actually defective because I knew what the true distributions were. So the real issue here we're getting to is Cpk is, we talk about it as Cpk, but it's really understood to mean a percent defective of a normal distribution. So how did it do? Well, I toyed with a lot of ways to chart this, and we'll see a couple of them here. But what I plotted there was the difference between the predicted defective using the Cpk and what was actually defective, since I knew the true distributions. What you notice is the shift, up to a shift of 2 standard deviations between them, the Cpk was pretty close to it underestimated the defective rate, but not by much. But boy, when I went past the shift of 2 standard deviations, the Cpk dramatically underestimates the problem. So you feel really good when you're not. All right. Another reason to check for normality and check for good distributions before you use this. All right. Is this surprising, though? As 2 distributions shift apart, why could it be shifting from normality, I mean being a mixture distribution, but not really fail too much? Well, I got the picture in the lower right that what you're getting is a platykurtic distribution. Okay, and I even defined it there, but it's a flat top and short tails. If you want to remember these, it's like a plateau on the top. But in this case, compared to a normal distribution, it doesn't have as much probability in the middle, but the tails are also shorter because the extremes are not driven by a narrow distribution that's shifted. The opposite to this, if you care, is called leptokurtic, which means it's pointed in the middle with long tails and it's not as wide. And if you really want to get it, this is called the fourth moment of the distribution, or it's what the kurtosis number comes up when you take your basic statistics. Now, did you really care? Probably not, but it's interesting. All right? Why do we care again? Like, why are we even listening to this? A lot of business data is non-normal. A lot of it's mixtures. Non-normal is the next topic. Time data is non-normal. Delivery times, cycle times, outstanding time to pay invoices, lead times, delivery times. Those are all log normal, or for sure skewed data, non-normal, and you have to be able to handle them. Well, if you took some of the, I hate to say low end, but this more simpler Lean Six Sigma training, they teach you normal statistics and say, you know, it's normal because most of the world is normal. But if you go out there and try this stuff, it's not as normal as it seems. Also, I have in here yield data. You can use some of this with yield data, but realize yields and percents, even percents calculated from odd things, come up as non-normal data. So now we're going to see how that impacts CPK. I have a chart here. This one came from Minitab using the probability distribution plots. What I have plotted here is a series of different log normal distributions. I chose this for it because the log normal is extremely flexible in how its shape parameter drives the symmetry of the distribution. It's for the same reason we use it in reliability statistics often. I took a location parameter 2.2 and adjusted the scale from 0.05 up to 0.8. If you look at the picture, if you can see the little lines, at 0.05 and 0.1 for a shift, for a scale parameter, it looks pretty symmetric. But you can look at the ones that are sort of shorter. There is a lot of skewness in those data. If you've done a couple projects, you've seen data like this. Now, how normal is it? Well, one thing, because what's the tool we usually have to look at data? We test for normality. And I said normality is an assumption of the CPK, so if you were a good practitioner, you run out and put your data in, do a probability plot and say, here's my probability that it's normal. So we took the data and simulated and plotted the p-values. The percent of the time the p-value would be less than 0.05, or you would reject the belief of normality as you move the scale parameter. As you can see, with very small scales, the 0.05 and the 0.1, you still have a reject rate around 5%, so most of those would be considered normally distributed. But as the scale parameter shifts, even at 0.8, you still have a 10% chance of passing a normality test and believing that your CPK can teach you good numbers. But we're going to see soon that it really doesn't. All right? By the way, the Anderson-Darling test, if you're not familiar with it, it's the one Minitab uses, but it's called a small sample goodness of fit test. Now you should realize just from the name, it's good for small samples. Big samples, it almost always rejects normality unless it's perfect. And even then, random number generators will sometimes be rejected just because of the way the algorithm works. All right. So how well did the CPK predict the defect rates when the data became non-normal? So we'll just look at the shifts using the at-risk data, look at how it performed. I used 1.3 last time. This time, because of the way I simulated, I chose to compare a CP equals CPK equals 1 for my requirement, and then I tested how far off truth was from that. So I calculated the mean and the standard deviation from every one of the 4,000 samples and said, given a CPK of 1, what percent is really outside of it? So I would assume, given those requirements, that the defect rate should be 0.0027 or 0.27% if it was truly normally distributed. So what we're doing is we're failing to meet the normality test and see how it impacts CPK. What you have here is looking at the percent deviation from what you expect You can see as you diverge from normality, the error gets larger. It gets up to almost 3% defective when you really should have it. You're reporting a CP and Cpk of 1. 3% when you're expecting near zero. Now that's the stuff that your leadership is going to wonder what you're giving them. If you give them a good Cpk number and still have defectives. So I'm hoping you gain that from this discussion. But you notice there's a two curves for between 25 and a sample size of 50. Why are they different? Why is smaller samples actually worse? Well, if you sit back and think about it, standard deviations have an awful lot of variation, and at small samples, the variation in them increases. And so you get a lot more Cpks that seem really good with small samples just because the standard deviation came randomly small. So that's why it deviates. So again, it makes sense. The larger samples, there's less estimate of error. All right? Now I try to put those two together, and I know the charting isn't perfect, but you can see, though, that the probability of failing the normality test and the error in nonconformance track right together. Now, it's not a perfect relationship, but realize this is, again, reinforcing. If it's non-normal, Cpk is not a great estimator of performance. Now let's wrap up what I'm trying to communicate. Often we are ignorant of the assumptions, and they really are important. I hope I tested a couple of them so you can see it. With mixture distributions, which are very common, the Cpk underestimates your quality or your long-term compliance with specification. And the same with non-normal data, which is also throughout our world of doing process improvement. Cpk will lead to underestimation of long-term yields. I guess, why do we care? I will propose that for Lean Six Sigma practitioners, quality practitioners, or all of us that are probably listening, telling my company that here's how good I'm going to perform in the future and being wrong, and it's worse, that undermines our credibility of very good skills we have. So part of this take back is say, am I really telling my leadership the right answer using the Cpk in this case? So now we're going to wrap up. I tried to cover the theory, confidence intervals, which I expect were new for all of you. And if you were like me when I learned them, you're going, wow, I never thought about that. So that could be an interest. There's also about mixtures and non-normality. There will be available, along with this webinar, we've written a white paper that talks about this in a little more detail. It's got all the equations again for you. It will be available soon. You should be getting an email that tells you how you can download it. Because, boy, if you take some of this to your leadership and they don't understand, it's a hard sell. And if you'd like this stuff, we'd like you to be able to improve your own skills, knowledge, and be able to use it to better yourself in your job. Looks like nobody sent me a question. So I guess we're about it. I expect a little more discussion, but I'm going to assume that this is a lot of thought going on at what was really happening. There's a lot you can do with this. I only looked at some simple cases. Take away from this a couple things is you can test your theory using simulations. I used a powerful software named @Risk. You can do some of this on your own. But again, test your theory, see what you're really providing your leadership when you use your capability metrics. If you want to understand more about it, our resource center on our website, smartersolutions.com, it's got a lot of discussions about using statistics, about understanding what they mean, about some, I'll say, innovative leading thinking tools that allow you to better estimate your business performance. I think Forrest referred to it at the beginning. They called Integrated Enterprise Excellence, or IEE. A lot of neat stuff in there. And if you're interested, stay in touch with us. We will periodically be doing seminars like this, really getting practitioners or quality professionals to help understand what we're really doing. We've talked about bad data. We've talked about Minitab. We've talked about different tools, and we'll continue doing that through Smarter Solutions. That's really all I have right now. Thank you very much, and have a good day.